In simple harmonic motion, kinetic energy. Velocity of a particle executing simple harmonic motion is a periodic function of time. It is zero at the extreme positions of displacement. Kinetic energy is given by K is equal to half mv square is equal to half m omega square a square sine square omega t plus phi is equal to half k a square sine square omega t plus phi. It is also a periodic function of time, being zero when the displacement is maximum and maximum when the particle is at the mean position. Potential energy. The spring force F is equal to minus kx is a conservative force with associated potential energy. U is equal to half kx square. Hence, the potential energy of a particle executing simple harmonic motion is Ux is equal to half kx square is equal to half ka square cos square omega t plus phi. Thus, the potential energy of a particle executing simple harmonic motion is also periodic, with period t by 2 being zero at the mean position and maximum at the extreme displacements. Total energy. Total energy of the system is E is equal to U plus K is equal to half K A square sine square omega t plus phi plus half K A square cos square omega t plus phi is equal to half K A square. Hence, the total mechanical energy of a harmonic oscillator is independent of time. Oscillations due to a spring. A linear simple harmonic oscillator consisting of a block of mass m attached to a spring. The block moves over a frictionless surface. The box, when pulled or pushed and released, executes simple harmonic motion. Hooke's law states that a system, when deformed, is subject to a restoring force, the magnitude of which is proportional to the deformation or the displacement and acts in opposite direction. At any time t, if the displacement of the block from its mean position is x, the restoring force F acting on the block is Fx is equal to minus kx. Here, k is the spring constant. A stiff spring has large value of k and soft spring has small value of k. For this system, angular frequency is given by omega is equal to under root k upon m. And time period of the oscillator is given by t is equal to 2 under root m upon k. Simple pendulum. A simple pendulum can be made by a small bob of mass m tied to an inextensible massless string of length L. The other end of the string is fixed to a support in the ceiling. The bob oscillates in a plane about the vertical line through the support. This periodic motion is simple harmonic for small displacements from the mean position. Theta is the angle made by the string with the vertical. When the bob is at the mean position, theta is equal to 0. There are only two forces acting on the bob given by the tension T along the string, the vertical force due to gravity. The force mg can be resolved into the component mg cos theta along the string and mg sin theta perpendicular to it. Talk 2 about the support is entirely provided by the tangential component of force given by theta is equal to minus L mg sin theta. For the system, angular frequency is given by omega is equal to under root mgl upon I. And time period is given by t is equal to under root I upon mgl. Since the string of the simple pendulum is massless, the moment of inertia I is simply ml square. Now, time period of a simple pendulum is t is equal to under root L by g. Damped simple harmonic motion. Sometimes the motion of a simple pendulum swinging in the air slows down and down. This is because the air drags and the friction at the support opposes the motion of the pendulum and dissipates its energy gradually. These are called damped oscillations. In damped oscillation, the energy of the system is dissipated continuously, But for small damping, the oscillations remain approximately periodic. The dissipating forces are generally the frictional forces. The damping force depends on the nature of the surrounding medium. If the block is immersed in a liquid, the magnitude of damping will be much greater and the dissipation of energy will be much faster. The damping force is generally proportional to velocity of the bob and acts opposite to the direction of velocity. If the damping force is denoted by Fd, we have Fd is equal to minus Bv. Forced oscillations. When a simple pendulum is released, it oscillates with its natural frequency omega, and the oscillations are called free oscillations. All free oscillations eventually die out because of the ever-present damping forces. When an external force maintains the oscillations, then these are called force or driven oscillations. The external force is itself periodic with the frequency omega d, called the driven frequency. The system oscillates not with its natural frequency omega, but at the frequency omega d of the external force. Resonance. The phenomenon of increase in amplitude when the driving force is close to the natural frequency of the oscillator is called resonance. Let us understand with an example. 5 simple pendulums of different lengths are suspended from a common rope. The pendulums 1 and 4 have the same lengths and the others have different lengths. Now, let us set pendulum 1 into motion. The energy from this pendulum gets transferred to other pendulums through the connecting rope and they start oscillating. The driving force is provided through the connecting rope. The frequency of this force is the frequency with which pendulum 1 oscillates. The response of pendulums 2, 3 and 5 are: they first start oscillating with their natural frequencies of oscillations and different amplitudes, but this motion is gradually damped and not sustained. The response of pendulum 4 is in contrast to this set of pendulums. It oscillates with the same frequency as that of pendulum 1 and its amplitude gradually picks up and becomes very large. A resonance-like response is seen. Did you know? The potential energy is minimum at midpoint of motion and at maximum displacement, the potential energy is maximum. The rise and fall in sea level is because of tidal forces, and the tidal current that is created is an oscillating moment. In 1656, the Dutch scientist Christian Huygens built the first pendulum clock. This was great improvement over existing mechanical clocks. Their best accuracy was increased from around 15 minutes deviation a day to around 15 seconds a day. Summary. Let us summarize what we have learned. The motion which repeats itself after equal intervals of time is called the periodic motion. If a body moves back and forth repeatedly about a mean position, it is said to possess oscillatory motion. The number of cycles completed in 1 second is called the frequency of oscillation. The change with time of any physical property under consideration is called displacement. Simple harmonic motion is a periodic to and fro motion in a straight line about a mean position in which acceleration is proportional to displacement and is always directed towards the mean position. The total mechanical energy of a harmonic oscillator is independent of time. When a simple pendulum is released, it oscillates with its natural frequency omega, and the oscillations are called free oscillations. The phenomenon of increase in amplitude when the driving force is close to the natural frequency of the oscillator is called resonance.